In this particular video, we are going to do a convolution neural network for sentiment analysis. So building a neural network for analyzing text. An opportunity to combine your knowledge and a bunch of the code that you have created in previous videos all into one. So let's give it a go. All right, so we're building a feed-forward network. Information is going to be shared from input to output and go through. Then we are going to do back propagation, where we're going to go back through the model again after we have adjusted the model weights and bias. We have tuned the parameters to improve the model, and the number of times we go completely through the network is what we call epochs. So we're going to have to make some choices in terms of what we're going to do to build our network. We are going to do sentiment analysis, so we're actually going to use Word2Vec. And Word2Vec is a very large file where we already have a pre-trained algorithm to help us identify vocabulary lists so that we can take our information that is text and the frequencies that are attached to the words in our text and compare them to the Word2Vec vocabulary lists, as well as to then identify whether or not they're more positive or negative in sentiment. So to build our convolution neural network, we've got to make some decisions. We're going to do what type of network. We're going to use a CNN. We got to decide on the size of the data set. We are actually going to reduce the size of the data sets that we're dealing with here simply because we're doing it in Google Colab, which has limited ability because we are using basically free access to other to cloud computing. And so when you have much bigger data sets, you need to pay for that extra cloud computing because it takes a lot of bandwidth. So you're either paying for the more formal version of Google Cloud or doing it on your own device. And so then you're running Python in, say, your Visual Studio or Microsoft Visual Studio, for example. All right, so we need to decide on the size of our data set. We'll look at that in just a moment. We need to decide on the proportion of training to testing data. So what portion are we going to hold out to be the test? What are our inputs? In this case, we're going to be inputting a bunch of text. And the output we want here is whether the sentiment is positive or negative. We need to decide on the amount of hidden layers we're going to have, how many epochs we're going to have, and our activation functions. And so in our previous videos, we have talked about different types of activation functions and when they are appropriate. The TAN function is used for outputs that are classified as strongly negative, neutral, or strongly positive. So we can use the TAN function. ReLU is used often for CNN. So we'll look at that as well. And we'll take a look in terms of what we created. When we do design a neural network, we have to specify a layer for input. We'll have dense layers that will specify that activation function. Because we are doing natural language processing, we're going to have embedding functions. There are other functions you might choose to have for masking, for example. What we're going to do is we're going to do what's called padding. And with padding, what we're doing is saying, okay, well, when it comes to reviews, there's not the same number of words in every review. So you have to go essentially by what could be the longest review, and then we pad the rest by adding a bunch of empty information into it, and extra values that that don't actually impact the model itself, but allow us to deal with the fact that the length of the data isn't the same for every review. If you have a masking layer, then that helps to address when the neural network should recognize and when to ignore padded values. Okay. When it comes to convolution layers, when we did our image processing with CNN, we did the convolution two-dimensional, and this looked at the relationship between pixels and other nearby pixels within images. In this case, we are using a one-dimensional convolution layer, and one-dimensional convolution layers can be used with time or forecasting models to represent lag, although we often will use just a recurrent neural network instead for our forecasting models. And so sometimes you see that convolution layer there in a recurrent neural network. In this case, we're using natural language processing, so we want to represent the relationship between nearby words in a sentence. We are doing it in a simplified feed-forward process, so it's not going to have the amount of information about the relationship between words that we would in our recurrent neural network type models. So it's a bit more simplified, but we do need to take into consideration the relationship between words that are next to other words. Okay, we're just not considering how many distances apart of words, which the recurrent neural network with the long-term, short-term memory can capture. All right, we can pool, so we can downsample to adjust. We can use max pooling and global max pooling to bridge the gaps between layers. And we can flatten to convert multiple dimensions or drop out if we want to address overfitting. In this case, we are dealing with our text. So we are going to go, let's just accidentally opening files here that are all over the place. Let's just jump forward while we're talking about activation levels to this. Then we'll go back through all the processing. There's a lot of processing. All right, padding. Okay. So what we're going to do when we build this is we're going to use flatten and dense, and we're going to use max pooling, and we are going to do our convolution one dimension. So just like we saw with our image processing, after you do a convolution layer, you want to do a pooling layer. So we'll have those two are often tied together. And we'll use ReLU as our activation function in the middle here. And then we'll use our sigmoidal function as we look at what's the probability that it's positive, what's the probability that it's negative. Okay, so we're actually going to use the sigmoid function here instead of tan. And you could set this up differently and use a tan function instead. All right, so embedding layer, we're going to need that because we will need to vectorize our information. So we'll have to add that embedding layer. Okay, so let's start from the beginning. All right, so first, what packages do we need? We are going to use train test split. Just make sure in the last video I had removed or not done train test split and I left the package in there. Oh my goodness, somewhere in here. I believe we're using train test split somewhere. Yeah, okay. So we are using our train test split to separate out our information. With our forecasting, with our time series, we were separating train and test by hand. So just making sure I wasn't separating them out by hand anywhere. Okay, so we are then going to have our standard scaler to help with our data. Although I don't think we're using that anywhere. So I think that's another one that I added, but then there's just the standard ones you put in, but I don't think I actually ended up using it. So we'll take a look as we get through rather than me scrolling back and forth and making everybody seasick here. Now, what we do need is we need to import word2vec. So from gensim.models.word2vec, import word2vec. Now, word2vec is a big file that you actually need to download and put somewhere. So I'm just going to show you, if you're working through this with us, you can find the workbook at drstephpowers.github.io/BIA. We are currently here in neural networks, which is where you'll find the Python workbook. Now, when it comes to word2vec, word2vec is a 3 gig file. So hopefully you have some space on your Google Drive if we're doing this in Google Colab. But download this and then dump it into your Google Drive if you're running this along with us. And then, if you got to free up space later, you can always remove it. But this is the data that creates an algorithm that tells us here's keywords. And we need that information to run this analysis. So this giant data set we unfortunately have to have available to us. And because it's so big, no one has a built-in kind of link in where you can just URL it. and have it appear within your code. Unfortunately, it has to live somewhere with you. So that's what this is here, is this big word2vec that we will call in a moment, but the actual package to use it is this gensim.models.word2vec. Okay, we're going to load in our neural network sequentially in terms of how we load in the layers. And so we need to have this import sequential. We can choose the different optimizer to deal with gradient descent, Atom, SGD, RMS prop. I think I have Atom running here. We can, I think I've put in R squared here, but this is not actually relevant. I don't believe so. Or maybe, yeah, no, because I think we're using accuracy. Yeah, so this R2 score, you don't need it here. What I often do is just have a big long list that I use, kind of paste it for all the different ones. What you will need is you will need tokenizer and our one hot coding and our pad sequences. So this ones are going to be specific to analyzing text. Then we can have different layers. We looked before, we're going to do some dense and flatten and embedding, convolution one dimension, and max pooling one dimension. So you do make sure you're running all of those. Okay, all right. We're going to be working through a video game data set. You can find the link to the video game data set here. You can also get it from the large data sets here. This one is the second half, the other version of the video game data set we've looked at before. And this particular one includes the actual text reviews. It is currently in JSON format, so we need to import that. So we're going to import JSON. And we are then going to use this process to convert a JSON into a data frame, create an empty list here, and then we're going to call our JSON file. So this is where we put it into our own Google Drive, link and mount our Google Drive, and then we can call it, this R is that it's read only, and that the information is loaded by line. So this JSON.loads line is specific to how the JSON itself is formatted, and this one has the information by lines. Then we use JSON normalize to convert the data in, and then we can call the table itself. All right, so now we can normalize it and then call it as a table. All right, so what we get here when we load this in is that we get review text. That's the comments, the reviews of these video games on Amazon. And then we want this overall score. So on a 5-point scale, people have ranked how much they like the particular product. So we don't really need the rest of this. So what we're going to do is simplify this down by creating a new data frame that is just the overall and the review text. Okay. And I forgot what that command does. Let's just take a look at it here. So sorry, I was trying to remember what this is. What we're doing is we want to actually randomly generate. So one of the concerns that came out of analyzing the penguin data is that we found that the penguin data was put in order by penguin type, and so that highly impacted when we built the neural network trying to predict the penguin type, because we ended up with a really distorted, unbalanced model where all of one type of penguin was in the training data and like one of it was in the testing data. So it was not very balanced. So what I've done here is added this extra line where it's going to take a sample from this, and it's basically just sampling through and rearranging the rows is what this extra line of code here is doing. So you can leave it off. I've just done that just out of precaution in case that it has all of the positive reviews first and then all the negative reviews. And I can double check myself here because I'm actually going to simplify this down. This is actually a huge data set, And in Google Colab and with all the bandwidth this is going to take, I can't really handle 150,000 data points or rows of material. I'm really just going to simplify it down, and we're just going to go with 5,000 at this point. You can play with it being slightly bigger. But I just want to make sure as I look through it here that I have some negative reviews and I have some positive reviews. Okay, so just to double check us, let's do a histogram of those overalls just to see the distribution in this subset that we've created here. We can definitely see there's a lot more positive reviews than negative reviews, but I can see that there is, what is that, about 600 negative reviews, and then we have a good 4,000 positive reviews, and we have some neutral ones. So this is an unbalanced data set. We do have a lot of positives, not a lot of negatives, but we just want to make sure that we have enough negatives that it can actually identify when things are negative and positive, and not just assume by default, because if everything you feed it says it is a positive statement, then it's going to then say everything is a positive statement. So we want it to be able to catch the nuances. Now, we are going to need to do some one-hot encoding here. We are going to take this Likert scale, 1, 2, 3, 4, 5, and we need to turn it into two columns here. One that puts a 1 if it's positive, and the other that puts a 1 if it's negative. So what we're going to do is just create a second variable and replace the overalls with 0 for 1 and 2, NA for 3. We can ignore the neutrals here. And we can then do 1s for the 4 and 5. So if you ranked 4 and 5, we're classifying it as a positive. Okay. And in this particular model, we're just going to take out the neutral ones. You could leave them in which case you would put them here as 0s as well. So we could have 3, all this 0, and this is just positive, and we could have this here for all the negatives, and then we put 0s for the positive and the neutral. So you could deal with it that way as well. Initially, I was designing this a little bit differently, so I was just going to have one column here for positive, negative, but it's probably better to have these 2 columns to label it. And so I probably should have put this back to 0s. All right, so we're going to flag the ones that are positive, flag the ones that are negative. And then what we're going to do is look at, we've created these 2 new variables here that are our 2 columns. Here, because I was removing these neutral ones, I had used drop NA to remove them. If you were going to classify them as 0s, then you don't need this drop NA. Well, no, I take that back. You probably should still drop it NA if there is no, because if it's not rated at all, and I don't know if this data set has any, if it's not rated at all, then you would want to drop it. So you might want to leave that if you replace these with 0s. All right, so what we're going to do is take our review text, and now we need to actually pre-process the text. So what we're going to do is we're going to take this column here that's the review text and turn it into a list. And the first thing we need to do is we need to clean the text. So we need to remove any extraneous symbols. And this is the function we had created in a previous video. We're going to import re, and that's going to allow us to find these pieces in the text and sub in just empty spaces for them. And so this is, depending on how it ported in, it might or might not have this. I think this one might actually already be cleaned up on its own. But what we would do is have this function here for removing URLs, HTML codes, any kind of like /n whenever there's a return or a space. Those all have been turned into symbols. We want to make that all go away. So we define that function, and then we apply that to every part in this. So we take our review text and we apply it. And this part can take a while, which is one of the reasons we reduced the size of the number of reviews to make that faster. And then what we're going to do is create a new column where this new column is going to be the cleaned version. Okay, so we'll just take that list that's now clean and we will make that be a column in our table. Okay. So here we have our clean text and our positive and negative reviews. All right, the next step in the process we know from our text mining is that we need to tokenize. So we're going to import in our NLTK. We're going to use word tokenize. We're going to remove the stop words, and we're going to lemmatize as opposed to stemming. So we talked in a previous video about the difference between stemming and lemmatization. So let's import those packages. We download stop words. Some of these other ones I have here because I just kind of copy over. We aren't actually doing chunks and the position that a word is, so you probably don't need a couple of these, like punked. Probably just need the stop words, the words. All right, then we have a function for doing our tokenization. So if you recall, we're going to do, this is the function we had before from our text mining, is that we are going to we're going to import in that clean text. And then what we're going to do is we're going to use the English stop words that are built into the NLTK. And then what we're going to do is we're going to filter out so that if it's not in the stop words list, it stays, otherwise it goes. Then we're going to lemmatize, which is what is the base word as opposed to the stem. We're finding the word it is in. So like, so step and stepping, stepped. We're removing those ings, the eds, and going with the original word. Then what we're going to do is we are going to remove things that are digits. And we are going to make it all lowercase. So this is the function we have for tokenization. So we'll create this empty list, and then we are going to take our token creator, this function here, and we're going to take that list of reviews that we had previously, this list of reviews that we had cleaned, and we are going to process it through and have it give us the tokens. So token underscore review is going to be filled with all the tokens for the different words. This might take a while because each of these statements, right, each of these words has to be tokenized that's in each statement. I've made the number 5,000 and said I originally did like 50,000, and then you're taking like 10 minutes. So I've reduced the sample size quite a bit in order to speed this up. All right, so then we're going to add another column, and this one is going to be the tokens themselves. And so we have our new table here where we have our clean text, our tokens, and then our positive and negative labels. The next process here is to split the data into testing and training data. So we have our table, or our VG2, our video game table 2 here. And what we're going to do is we're going to split it, and we're going to do the 80-20. So 80% into training, 20% into test. Okay. And then what we're doing is we need to look at how many words we have. We're trying to look at basically building a vocabulary list so that we can compare the unique words that are in our test and training data to the words that are in Word2Vec to help us identify then, because if Word2Vec is already trained that these words are these types of sentiment, when we put them together, that's going to help us in terms of building our model and identifying with ours. So what we're going to do is we're going to create all training words, word for tokens in the train tokens for word and tokens. So we're going to look at all the words, right? And we want to find the length in that information and then find that vocabulary for the train. So we're going to do that for the training data. We're going to do that for the testing data. We're simply trying to create those vocabulary lists. And so let's take a look at one of these, for example. So the vocab for the testing one. So here's the vocabulary. Okay, bench, benefit, believed, began. Okay, so here we have all of our words. Now we need to pull in word2vec. Okay, so word2vec we're going to need from gensim.models import word2vec, which I think we had at the beginning. What we're actually going to be using is this keyed vectors. So we can't just actually compare words to words. We have to vectorize them. And so we want from word2vec is not so much all the words, but we want the vectorized versions of words. So we're going to pull key vectors. The first thing we need to do is we need to pull in word2vec. So this code here is telling it to go get the word2vec, that 3 gig file called Google News Vectors -300. This is training based on Google News to help identify positive and negative sentiment. And we then need to get it. So I need to set the data path to be where I put it. In my Google Drive, it is in BI Handbook folder, and inside that it's in the Chapter 10 folder. So you can see here that I'm getting the Google News file and where I'm getting it from. So you would trade out this line and this line here to be where in your Google Drive you have put it if you're doing this in Google Colab. If you're doing this outside of Google Colab, then you can store it in a folder somewhere on your computer. All right, so I need to import the packages, and it's really this keyed vector is the one we need. I think we already had imported the word2vec previously. Okay, so then let's pull in this giant data set. And because it is huge, this step can take a moment. All right, so we have now our word2vec is now loaded into our system. It says it took 1 minute and 19 seconds. Then what we need is this function here, or it's kind of a function nested in another function, to pull from word2vec the relevant information to our particular reviews. So what we're going to do is we're actually going to call the function get word2vec embeddings, which is going to use that word2vec model, okay, which is the keyed vectors. And it is going to then take our training data. And what we're essentially doing is we are using this function get average word2vec, and it's looking for, here are the tokens, here are the words that are in our training data. Are they in the word2vec system? Are those similar tokens there? And then if they are there, then we want the vector that goes with them, or the embedding that goes with them. So the first part here is to come up with, are all of your tokens in the system? And we don't want it to generate missing tokens. We simply want to, if the word or the token is in our training data and it's in word2vec, then what we're going to do is we are then going to apply to that and get the word2vec vector. So all of this, just leave it as is simply to pull that information, the embeddings, from the word2vec. Okay. So we are going to use word2vec model and our training data to generate the embeddings for our training data. So let's load that function and let's get our training embeddings. All right, let's see. Might be too big to show it to us. Take forever. Give us a huge amount of data. Maybe. We done or crushed? Okay, here we go. So what we can see now is we see a bunch of numbers. So what we've done is we have vectorized our text, our tokens have now been turned into numbers. So there's a lot of numbers. And so there's a whole string of, or an array actually, of numbers for each of our reviews. I'm just gonna. So now that we have tokenized now that we have turned into vectors each of our tokens, now what we're doing in our next step here is we're combining it into essentially strings of vectors for the actual like entire statement, right? So we have vectorized and tied to our word to vec each word. Now let's combine the words together, but not as words, but instead as numbers. So taking all of those and combining them into kind of the whole sequence that goes with a particular review. So what we're going to do is we're going to use tokenizer inside that comes from the Keras TensorFlow. And the number of words is going to be based on the location or the amount of vocabulary we have in our training data. And we are going to take that training data and turn into a list, and then we can make it a sequence, right? So we're going to be putting all of those together. And then we need an index for that as well. So all of this here is manipulating our training data to prepare it in. And then the last thing we need to do for that training data is to add the padding. When we talk about padding, we're talking about, so now that we have created, Okay, so just to backtrack here, the word to vec helped us vectorize words. So turning words, we took words, we turned them into tokens. We took our tokens and we vectorized them. We turned them into numbers. Now we're taking those and turning them into sequences of numbers to represent the entire review. That's what this is here. And then we have our padding where we are adding extra space essentially to make the length of the reviews in terms of the length of the sequence of vectors to be the same for all of them. Okay, so that's what this is here, is it is going to add padding to that sequence of tokenized, vectorized data here. And we're going to set what the max length of that sequence should be. So here you can see we have said that there really shouldn't be more than 50 words in a review. And so the max sequence length here as we do padding is going to be 50. So we've said the maximum length of the sequence is 50, so maximum 50 words in a review. We then need to consider what is that in terms of embedding dimensions. And if we are looking at that each word is a vector, so a set of numbers, and then we're adding all those in a sequence, what is the total dimensions? Here we have embedding dimensions of 300. If you have 100,000 sentences kind of in total, then 50 to 100 for your embedding dimension. If you have more than 100,000 sentences, then you want to go higher. So instead of 50 to 100 for your dimensions, you're going up to about 300. And I think originally, I had a lot of data here. I've reduced it down to 5,000 reviews. And the question is, how many sentences are in those reviews? And probably not to the point that we need an embedding dimension of 300. It's challenging because you don't want to be too low or too high with your embedding dimensions. You want to increase your accuracy of your model with lower dimensions, but then complexity of your data leads you to higher dimensions. So, somewhere between 50 and 300, depending on what you got here. So what do you do with this? All right, so we have this information, and what we want to do is we want to take that and put it into our padding. So we're adding that extra space here based on the maximum length of a review being kind of 50 words, and then translating that into the embedding by creating these embedding weights. And we create the embedding weights for our training data, starting out with just kind of an empty set of zeros for the length of the training word list. And then and then we have those dimensions, right? So we've added in here to make this just an empty list that is 0 for all of the index, and then times that 300 dimensions. And this creates then weights that are tied to our word2vec model. So we're going to pull those embedding weights that have the amount or all of these the vectors here for our rows of data. So padding is tied to we'll have those embedding weights for the emphasis we put on those. So then what we're going to do is we're going to turn our text to sequences for our test data as well. So that was all prep for the training data. For the testing data, we also are going to need to pad it and to use this text to sequences that we used up here, the same approach that we had here. That way we can actually test our data later. So less that has to be done in terms of padding. I think we actually talked about previously, like one of the challenges when it comes to padding. Where did I put that? There we go, masking here, right? So padding is used in our, so there's a difference in terms of when we use padding in the testing versus the training data. So that's why we're treating it differently in terms of here we are doing this padding here with the training where we need the weights, and then here we have just some padding for our test data. So a little bit different how it is treated. They don't have this extra step here. All right, so where am I in the grand scheme of things? All right, so padding here, embedding weights. Now we're converting for our test. We're going to do text to sequences and the padding there. Now, one other thing we're going to do is we're going to put labels onto the data. So our label names are tied to those two columns that we had, positive and negative. And so for the training data, we'll call ytrain. That'll be our training data with the label names. And then for our xtrain, we'll use our, what we just created here, which is the padded version. What we created just here, which is the padded version of our training data. So we're prepping it to put it into the neural network. All right, let's get to our actual neural network here. We're going to load things in sequence, so we're going to add layers. So that's why we're doing model equals sequence. Anytime we are dealing with words, we have an embedding layer. This embedding layer is going to take the length of our training word index, so our list of our key words that are in our training data. Our output dimension is going to be that embedding dimension that we had set at 300. Our input length here is going to be that max sequence length. That is the max number of words in our review, which is 50. And then we have the weights for our embedding, which we got from that word2vec. And that's a training embedding weights. Okay, so we need that embedding layer added here. So we're defining it first, and then when we do model.add, we're just adding it in. So rather than have it be part of all of this here. Then what we're going to do after our embedding layer, which had our input taken care of in that embedding layer, we can now deal with our hidden layers. And so we go back to our convolution one dimension. Because we are looking at the relationship between nearby words, so that is at con1d. Okay. And our kernel size, or the size of our output space here, we've set at 8. We're using ReLU. So our output space is 32. We have a kernel size of 8. And in these cases, when we come to that output space, we're going to get smaller and smaller. We're going to, after we do our convolution one dimension, we're going to do some max pooling to kind of summarize and what that has found. Then we're going to flatten. And so when we flatten, we're converting this multi-dimensional element to one dimension. We're transitioning from these convolution layers to more fully connected layers as we're transitioning through. So this flatten is taking us from our hidden layers closer towards our output. And we have a layer here, another activation And then we are getting ready to output it using that sigmoid. And here you can see the length is the list of label names, or you could just write 2, because here we have our positive and our negative. So the way we've designed this system here is that the output is actually going to be 2. A probability it's positive, a probability it's negative, okay? As opposed to putting it all into kind of one variable. So if we're going to put it all into one variable, where that variable was, say, -1, +1 for positive for a positive statement, -1 for a negative statement, then we wouldn't use the sigmoid activation. Instead, we would use the tan one. So what we have here, I can't see it, but the tan function goes from -1 to 1. -1 to 1. And so we can use it for sentiment analysis because we have strongly negative, -1, neutral, 0, strongly positive, +1 as the outcome. So it'd be a single variable with is it closer to one of those 3, as opposed to the method we're using at the moment, which is to have it predict the probability of the 2. So you can go either way. All right, let's add that in. Let's compile this. We're going to use Atom for our optimizer. Because we are using sigmoid and we're predicting what's the probability it's positive and the probability it's negative, then we have the binary cross entropy is what we're using here. And so because of that, we can look at the accuracy. So was it correct in labeling that it was a positive statement? Was it correct in labeling that it was a negative statement? We can set the number of epochs. As we move through our model here, we can separate it out here, or we can put it inside. We have a lot of data, so we really can't handle a whole lot of epochs. I don't know, let's go up a little bit more. And that's the number of times that we go through. Then the other thing is because this is such a large data set, when we're processing word sequences of words, these big vectors, or sequences of vectors, we actually handle it in batches rather than dumping it all in. And so we can specify the batch size here. And there are other parameters that we can set, shuffle, validation. You can set those or leave those as is. And then we have our X-train, Y-train data. All right, so let's go through. And then we wait. Let's see how long it takes to do 5 epochs. Probably not as long when I had 50,000 reviews as opposed to the 5,000 I have in there now. So we could probably handle some more epochs than just 5. So notice we run these and it's just finalizing here. Notice that it's actually giving us a loss and an accuracy and a loss and an accuracy. Again, because we have had our 2 labels here, and so we are looking at the accuracy of either one. To look to do our evaluation, we do model.evaluate for our training data, and we run this here, and we can see that it's 98% accurate. Then to do a prediction, we can use, oh, sorry, that was the training data, not the testing data. So we would, the training data, right, that's what it was built on. Sorry, the testing data is what it was built on. The training data is what it was built on. So we expect this to be highly accurate. We really want to know is about the testing data, that the reviews that are not in the system. So what do we do with those? To deal with those, we are going to create a prediction. And so we have the test CNN. So let's just go back. This test CNN, our test data, it is padded, right? It is turned into sequences of those vectors. So we have it already prepped from the work that we did before. And so because it's already in that format, it's ready to go. We can set a batch size for how it's getting processed through. We don't need it necessarily to be as small as what we had for the previous batches. So we can run this. And then what we get here when we look at the predictions is this is the probability that it is positive. This is the probability that it is negative. So what we want to do is convert that like we did with our binary classification MLP regressor or classifier. And so we'll set label X as 1 and 0 and call this whatever you want. And then we're just looping through. As it goes through these, it's going to look for the maximum of these two numbers. And then it is going to use that to determine whether or not the label should be a 1 or a 0, 1 being positive, 0 being negative. So we can have it loop through this and apply these labels based on the maximum of the two numbers for each. And so when we do that, we want to figure out how accurate it is at the testing data. And so what we do is we compare the testing positive to when the label predicted that it should be a 1 and dividing that by the label predicted. When we do that, we get that the testing data is 88% accurate. Okay, so we've created a model to predict whether or not the review is positive or negative, and what you can do then once you've created this model and tuned it to the way you want, then what you can do is you can take new reviews, you process it here in terms of clean it, in terms of tokenize it, in terms of combining it, all of those, and then tokenize, vectorize, and then turn those vectors into sequences for the reviews, add the padding, then you can put it in here and then you can get the prediction here. So texting requires a bunch of processing because we have to convert it into a form where it can be treated like numbers for the actual analysis and the model to be done. So a lot of the language piece and the part that is the work is in prepping it, cleaning it, tokenizing it, vectorizing it, all those components to get it ready for the actual analysis. Now, when it comes to this, we just did this for the video games, but you could give this a try on your own for the pet supplies example. We've looked at the pet supplies data set before, and you can get it from the original source here, or you can go and download the pet supplies data set. There's a different version than the one we looked at previously. The previous one just had the ranking. This one has the reviews, and so we are looking here at the text in this particular case. So try creating a model similar to what we did. Play with the different hyperparameters to improve your model in the process.